So I was interested to see what was inside this Philips Compact Fluorescent 11 watt ancient compact fluorescent, and was surprised that it had a couple of MOSFETs in it. So it's then led me to go and take a look at some of these other compact fluorescents. Now obviously that's a name brand, and MOSFET, I mean they're high voltage MOSFETs, so they haven't got a very good RDS on. I think it's 3 ohms, I think, when I looked it up. But I then went scavenging through some of these cheapies, and so far I have not found another one that's using a MOSFET. These are all basically the same design. The old 13003 transistors. These ones, it's an insulated, it uses 2 of them, 13003s. This is a 13003, but it's using the more dangerous one. That one was this Reliance. So judging from that, I'd say it was probably 48th week 2001. So that's using the dangerous metal package. Well, more dangerous. I mean, theoretically it's all enclosed in there, so if you're going to get it open, there are other things you need to worry about. But anyway, and these ones, so that was an 18 watter, old cheapo, yeah, 18 watt, and that will look like it's 2002, 32nd week. It's a 15 watt Reliance. It's 2030, same week, well, 32nd and 38th week of 2002. So another Coles 15 watter. That's Reliance. I thought I already opened the Coles. So that's get it open. So what I did was I jimmied that off and cut those things, and then put the tube somewhere safe, in quotes. So that's got my safety glasses on. Obviously I'm not going to reuse it. Well, I might reuse the components out of it. That's the reason why I'm pulling it apart. So, because those, you never know, MOSFETs are MOSFETs. The other ones came out a lot easier. They were much more brittle. Which, there we go. Which is to be expected, because the compact fluorescents basically produce ultraviolet, and so most plastics become brittle. And this looks like it's going to be another 13003. Good. 13,002, if I'm not mistaken. Yep, 13,002. That strobing's not going to help anyone. So, bipolars yet again, and that one was 2006. So 06, 8th week 2006. So they're still using bipolar. So that's another 2006. Let's leave that. That might be interesting. 2001, probably not going to be interesting. Now this one's weird. I can't remember exactly when, but the numbers on here suggest that it was 1992, and that must have been right in the early stages. I mean, this one's got a separate, the compact fluorescent has a separate assembly that goes in. I'm not sure they've still got it around. Yes, so, and that basically clicks into there, and so it sort of explains why it says it uses 10 watts with a 13 watt tube. Yeah, 13 watt Osram tube. So being that sort of modularity, one might expect that the date codes are correct, 1992. It's certainly, I think it's plausible. So the issue now is how hard. It's really thick plastic. I don't know whether I'm going to be able to get that open on camera. No, I can't get a grip of it. Alright, let me come back. So, as Big Clive would say, a vice of knowledge. Not that I'm trying to spoof Big Clive. Even though we are very similar, I think we're the same age. Up until recently, I think we had the same circumstance. Although my mum just passed away. I don't have to worry too much about stuff flying out, all this rubbish, this glue and crap. So I'm not sure that it's okay. I think what I've been cracking is all of this plastic here and not the seal. And I don't know where that other piece went. Yes, I do. Can't see that. 13,003. So you could say, apart from cosmetics, the basic design hasn't changed much. Since 1992. Oh, so that's using 2, that's using 1, that's using 1. So I suppose I should show. This one's a 2001 10 watt. Humongous thing for a 10 watt. That one's a 2006 15 watt. So typically what I do, because this stuff is all brittle in here, you can usually break it loose like that. It's pretty much chalk by this stage in the game, and you don't want to be, you want to be careful when you cut, because they have little nipples. It's a different chip, different transistor. DK53. Shenzhen Engai. Anyway, if you bang this into Google Translate, it tells you roughly what they're talking about there. And you can see it's an NPN, yada yada. Not quite as high. PCE. I don't know, I wonder whether they've reversed these two values anyway. Yeah, HFE's not that great either. To be expected, but you can show you what their website is there, and if you go to their website, you can see that they've got the 13,000, so 3 is in the various packages, and the DK one was there, and as you can see, it's the wrong package, but that's the only one they list on their site. Anyway, so what I wanted to do was to reverse engineer the circuitry, at least some of it, and I recalled that I had done that before, so I went through those, and then saw the one for the oldest one that I don't know about the oldest one, but I'm pretty sure it's damn close to being the oldest one, the smart lamp one. It had this unusual bit of circuitry in it, which I've reproduced here. Just the beginning part of it. So you've got your mains coming in, a 5.2 ohm resistor, basically acting as the fuse I'd expect. Rectified, full way rectified, and then these tiny capacitors here, 330 nanofarads. Nose to tail, like that. So effectively across there you've only got half that. And then you look at this and you think, what is this? Now this particular thing is an optically triggered TRIAC. And it's like, what's this all about? I mean, effectively when this TRIAC's off, this should be like half voltage between the plus and minus there, and it switches on. Let's say that's positive, and it switches on whilst it's on its positive peak, then whatever voltage is across here is going to get, so you're going to get a spike at this point here, right? It's going to reverse bias these. You're going to get and at the whatever energy is in there, the charges is going to get, and there's not much charge in there either, so it'll just be a spike. So what triggers it? Yeah, it's like crazy. What's this? 56 ohm. So alright, so if I have a voltage, an appropriate voltage across here, that should switch on and trigger that. So how much current are we talking there? Well, let's get the specs on this optical device. So this is one from Lighton. The original one, I suppose, was the Motorola one, and it's like random phase opto-isolated tracker. What the hell do they mean by random phase? Anyway, so looking at the Lighton one, look at the specs here. So this is our electrical optical characteristics. So input forward voltage. This is obviously the voltage across the LED. So 1.15 volts with a forward current of 20 milliamps. And the voltage reverse is 6 volts. Absolute maximum ratings. Yeah, the reverse voltage can only be 6 volts and it breaks down. Begins to break down. So this is mains here. So I've got to be damn sure that it's not going to get reversed. there's definitely no reverse blocking. Damage the thing anyway. So okay, so this is our lead trigger current. That's what's required to latch the output, and we got the 3021, so maximum of 15 milliamps. That's quite a bit of current going just through the LED to trigger it. So let's look at the circuit again. Alright, so if we work it out, let's go worst case scenario. So let's get the calculator. Tools. Okay, so what have we got? 15 milliamps. Times 27 ohms. It's going to give us 0.4 volt plus the 1.15 volts of when the LED is forward biased at that current. It's 1.55 volts, so we're going to have 1.555 volts across 56 ohms is, divide that by 56, 27.7 milliamps plus our 15 milliamps, so we're up to 43 milliamps. So it's a 15 watt bulb, so 15 watts, and it's 240 in Australia, so 62.5 milliamps. Well, it's definitely going to get activated, and you can see, apart from the inductors, it's also going through this stuff. So we've got, so it's a 4.7 microfarad. Interesting. So when that switches on, it's going to provide, it's not a striking circuit. No, it can't be, because that inductor's going to, well, they're bypassing it. It could be the striker to get the cold, like the fluorescent tube to start conducting. Or it could be some sort of, see, the thing I noticed about that particular smart lamp was that it had a claimed power factor of about 0.8 from memory. Power factor 0.8. That's extremely unusual. If we look through, yes, so this CFL harmonics, this guy does it, and I actually did some testing on my own power factor meter here on some 24 watt CFLs, and they were much worse than 0.8. So you can see compact fluorescence. So if it's 15 watt, and they're talking about power factors of 0.2. So could this circuitry have something to do with power factor correction? Interesting. Oh, that's the other thing too. So we've got 4.7 microfarads. So it's a full wave rectified output, and this is our peak to peak, which is how you work out. So it's 62.5 milliamps. If we divide that by, open brackets, 2 times frequency is 50 hertz times the capacitance, which is 4.7 exponent negated microfarads. Wow, 133 volts peak to peak ripple. Yes. So yeah, so this is interesting. See this current waveforms. Where did I see that? I thought I saw that was on. Yeah. So this particular graph here shows you of a typical compact fluorescent. So in red we got our mains voltage coming in. So obviously this is started long ago, but if you were to start it, you would rectify, the current would follow until the reservoir capacitors got filled, and that would just no more current. The voltage would just stay there, so the current would just go up to there and then basically stop at the point when the diode becomes reverse biased. So in here, what they're talking about is this is current. So as you can see, this current here is the point at which the lowest part of your ripple voltage. So we had 130 volts peak to peak, which explains why it doesn't happen right there. It happens right down here at the lower end of your ripple, and you get massive current draw, and the current dies off until it reaches the peak, and then there's no more current until it hits the negative portion of that from the full wave rectification there. So you can understand how those spikes, and more importantly how you get a lot of noise because of these switch mode type electronic high frequency designs, like of computer power supplies, and obviously compact fluorescence as well. So yes, I think an experiment is in order. I think what I'm going to do is I'm going to cut the tracks at this point. I'm basically going to, and I'm not going to run mains in here, I'll just run it on just lower, like I've got a transformer with multiple taps on there. And I'll vary the load here and see if I can get this thing to switch on and see what it does. Let's have a bit of a tinker. Oh, and one extra thing is, whilst Wikipedia has quite interesting information, this guy here deserves a bit of a shout out. Just bear in mind that the waveforms shown here are a combination of simulations and actual measurements. So I haven't seen anything that was too out of, so it seems quite good, reasonably accurate as far as I can tell. But the main thing is he has some example circuitry, and whilst I haven't seen this one, some of these ones are very close to the ones that I've redrawn. So worth a bit of a look. So the circuitry I'm going to do, so that's it sitting down there. Oh, and this is, I just got a mains transformer with multiple taps on there and all rigged up so I don't electrocute myself within reason. So I've got using two scopes on the channel. So what I'm got the scope at the moment. Where have I got it? So what I've done is I've put a resistor in series, 1 ohm resistor. So let's just whack it in there, and I've just made that the ground point, and I've just got that on channel 2. And basically what I'm doing there is I'm measuring the current. So the voltage that's developed across the 1 ohm resistor, it will be proportional to the current. And I've got channel 1 wired up to pin 6, so it's on this side of this resistor. So whatever voltage we see there in comparison to between here and there is what we will see. So currently we're drawing 1 milliamp, and as far as I can tell, based on that the yellow one there, there's that TRIAC is not switched on. So if we increase the load current, so by increasing the load current that I'm drawing here, I'm increasing the amount of voltage drop across this 56 ohm resistor, which is then providing the bias to switch on that LED. So if I increase the load current, take it, so I need to reduce the resistance. So, okay, so that's on the 24 volt tap there. So that's on the 12 volt tap. Move it to the 20 volt tap. There we go. So that's switched off. So you can see we've got 1.4 milliamps. And as we increase, we're looking at channel 2, remember? This figure here. There we go. So it was around about 2 milliamps. Interesting, there's quite a bit of hysteresis there. So you can see that, there's that spike. And if we look at that, so when it was off, we basically had just had an AC waveform, half-wave rectified waveform there. And now we've got this funny business going on here. So it was centered about 0, and now we're getting negative spikes in there. On the TRIAC, and as I increase the load, what happens? Okay, so if we go down another resistor, okay. That went away, did it? Yeah, okay. So 3.4 milliamps. And it goes away at 3.2 milliamps. Almost, yeah. Interesting. So I moved that up to the 30 volt tap. Drawing 7.8 milliamps. And that spiking thing has gone away. Spoking. Yep, she's pretty hot. So this is the one that I hand drew. This is probably like the umpteenth variation thereof. So you can see I didn't draw it as a TRIAC, I just drew it as a dip package. This needs more work because it's not complete. That was the other thing. There's no heating elements on this one. It's just 2 pins. Like if you look at these ones, these are actually got little heating elements. So they are kind of like an old, like a valve tube. And these are, let's unplug all of this so I don't fry myself. So if we have a look at that, it's pretty low. I should use the LCR meter, I think. 7 ohms, 6.9 ohms. So just like on the old school, you know, the long flat tube with the magnetic ballasts, the inductor type ones, they have the heating elements. So you basically warm them up, and the higher temperature means that it can start to emit electrons and produce the plasma at a much lower striking voltage. So they've continued to incorporate that. So this is basically just a tube that's been wound around and around to do that. Joined here. Okay, there's another design. That's joined. Yeah, they're all joined. So another one if I can get access to the leads, maybe. Yep. 6.6 ohms. Another one. Can't get a grip. Anyway, so what do you guys reckon? What do you think that circuitry is for?